3.2, reduce problem size by half. So another special case. But this time we know how much the problem size we can reduce by approximately half. Let's look at the example. Question. Problem number 10. Count binary bits. This question. Given a positive decimal integer n, find the number of binary digits in its binary representation. We can do binary conversion. After that, you just count the number of bits in its binary representation. So pretty simple. But here, we want to use the recursive algorithm to solve this problem. All right, now let's do the analysis. First, we want to look at the general form of the binary representation. It's like this. Based on your discrete math, you have this representation. But here we should assume the most significant bit, b sub s, that is the most significant bit, is not equal to 0. So it can only be 1. 0 or 1, so it must be 1, most significant bit. Then we can write our answer representation s plus 1. If we count the number of bits, right? We have this many positions. We look at the subscripts from 0 through s. That's s plus 1. Simple counting. So now we need to write S representation. What is S? In terms of n, right? In terms of n. Then we get the answer, right? So here, let's try to get the insight for this question. Here, we like to do the transformation to change the structure. Then we can get a recurrence relation. But you need to do the transformation first, or transform first. All right. Division operation. Because here you can see we use base 2. The base representation number, base is 2. So here we like to do division by 2. Division by 2 operation. So that's like this. Both sides divided by 2, but the left-hand side may not be integer, so we take the floor function. After we take the floor function, you can see the b0 part is gone. No matter it is 0 or 1, after we take the floor function, b0 is completely gone, right? Now, if you compare the two representation, these two, right? Compare these two, you can see you can get a recurrence relation, a simple recurrence relation. All right, so let's do the observation here. First, the least significant bit is removed. B0, that's the least significant bit, is removed. After I will do base 2 division. The number of bits is reduced by 1. We only remove 1 bit, so reduced by 1. But the problem size is reduced by approximately half, because it is the floor function of n over 2, approximately, almost, so we can treat it as half. half-size reduction. Yeah, so that's the observation. So with that observation, so we can derive the recurrence relation. Okay. We assume the number of bits, that's the function b rec of n, number of bits for problem size n. Then we do half-size reduction, right? The size becomes floor function of n over 2. So the number of bits for that smaller problem, after that, we need to add 1 bit back because we remove that least significant bit. So this 1 bit corresponds to that least significant bit. And we have the base case for 1, that number is 1. Yeah. So we have a whole recurrence relation problem. Recurrence relation, so this problem, we need to solve. Okay? So when we solve, there are 2 ways we can do. First, we write a computer program, we can implement this function, find the value. Yeah. Here, let's do it here. Yeah. Pretty straightforward. So you can see, pretty straightforward. Yeah. But another way, we want to derive a formula for it. Can we get a formula, math formula? Because if we have the formula, we do not need to do, this implementation. If we have formula, we just evaluate that formula. How about that? So that will be faster, right? Yeah. All right. Anyway, we will do next round analysis. This round, we want to count the number of additions we need. Yeah, because when you do the recursion, you need to add 1, right? How many times you need to add that 1? That's the basic operations we need to do. Yeah. All right. So here you can see in our implementation, when we do n over 2 floor function, basically we just do left shift operation. You have the, the binary point, not decimal point, binary point. You shift that point 1 position to the left. That's the division by 2, because you also do the truncation, right? Yeah, shift, you do not include the fractional part. So that's the floor function. Yeah. That shift operation is very fast. It is faster than addition. Yeah. But here, we treat addition as the basic operation. Yeah. All right. Now we define a function, a of n, represent the number of additions. So we want to calculate number of additions, a function. Yeah. You can see for the a function, we have the similar recurrence relation. Yeah, similar. Okay, yeah. Yeah. But, right. A of 1, so we still make the 1 not 0, right? Yeah, because a of 1, 0 plus 1, right? We treat as a 0 plus 1, although we don't have to do it. Yeah, but, just the 1, so we just take it, all right? Because in this way, the structure here and the structure of our original problem, the same, exactly the same. Although their meaning are different, but the expressions are the same. If we solve this problem, then we have the same solution on that problem, right? Yeah. So we just solve it, yeah, mathematically. Yeah. All right. How to handle the floor function? That's the tough part. Because in our formula, when we have the floor function, usually it's not easy to control it. So that's the hard part. So we like to remove that floor function. If the floor function is gone, then we will be very happy. Okay? Because we can do the normal operations. We do not need to consider the special cases, right? Yeah. Here, before we do that simplification, let's look at the floor function division by 2 cases, only 2. When n is even, we get n over 2. When n is odd, n minus over 2. So 2 cases. Yeah. All right. Next, when we try to solve the recurrence relation, we take one strategy we frequently used. So what's that? Start with a simpler case. Yeah. Here we have 2 cases. Which one is simpler? So we want to start with that simpler case. Okay. Yeah. Even case simpler or odd case simpler? Yeah. Yeah. Even case simpler, right? N over 2 directly. We do not need to do n minus 1 then divided by 2, right? Yeah. N over 2 directly. Yeah. That is simpler. So let's look at that case first. Okay? Yeah, simpler case. Next question. What do we wish to have when we work on problem size reduction? What do we wish to have? When I ask this question, we want to pick the best case we can have. That's the wish, right? You always wish the best, right? You do not wish the worst. Yeah. So when I ask this question, what do we wish to have? We try to get the best case scenario. All right? Yeah. So let's look at what do we wish when we do first round division by 2, we make n even. That's our wish. But we need to do second round division by 2, floor function. This time, we wish n over 2 even function. Then, n over 4, we do not have the fractional part, right? So that's the best case scenario. Yeah. And so on. We can do all the way down to the bottom if, for the best case scenario, you can imagine we like to assume n is power of 2. That's the best case scenario. If n is power of 2, you can see we have integer division without fractional part all the way down to the bottom level. That's the best we have. Yeah. All right, so now we just assume n equals power of 2, 2 to the kth power. Then k equals log of base 2 of n. New recurrence relation, we use k. Yeah. So we have this new way. Okay. All right, so now we need to find the answer. Yeah. So let's do the work. We list all the possible equations when we do the problem size reduction divided by 2, because we have a nice representation when we do division by 2. Yeah. So we have all these equations. Then we add up all these equations, 2 sides. We can do a lot of cancellation. So look out, we can do a lot of cancellation like this. Yeah. Yeah. So these 2 terms we can cancel out. Then and finally we can cancel all these terms. Let's add them up. The left hand side, a of 2 to the kth. Yeah. Right hand side, yk plus 1. Yk plus 1. Yeah. Look at how many lines do we have? Can you count the number of lines? How many lines do we have? Count by reference. Can you find appropriate reference you can use to count the number of lines? the exponent number from 0 through k minus 1, right? From 0 through k minus 1, that's k. K lines. Each line you have 1, right? K line you have that k. So this 1 corresponds to a of 1. So you have k plus 1. Yeah. All right. We can write the final result. A of n equals, we use n in our representation, 1 plus log base 2 of n with condition n equals 2 to the kth power. Next, we need to look at the general case. General case, because this power of 2 and 2 special. We want to have arbitrary n without any special format. So for the general case, at this point, we can only guess. We can only make our guess. When you see this formula, can you guess a reasonable formula for the general case? Because in the general case, log base 2 of n may not be an integer, but our a of n must be an integer. How do you make that non-integer representation to an integer representation? Force it to an integer representation. Floor function or ceiling function, right? Floor function or ceiling function. Here, do you like to use the floor function or ceiling function? Think about that. Okay. Here, a better guess is floor function, not ceiling function. Why floor function, not ceiling function? You can try some simple examples to see it, right? Simple example to see it. For example, when n equals 3, how about that? N equals 3. Because you don't want to choose n is a power of 2, right? You want to avoid power of 2. So not 1, not 2, so then 3. You try 3. When you try 3, binary representation, 1, 1, that's 2, right? You count number of bits, that's 2. So left-hand side, you get 2. Right-hand side, 1 plus log base 2 of 3. Log base 2 of 3. Floor function, that is 1. Ceiling function, that will be 2, right? That will be 2. And when you use 1, it's correct, right? 1 plus 1 equals 2. When you use 2, it's incorrect. So that special example, you can make sure you have a better guess. When you use the floor function, it is a better guess. Otherwise, ceiling function, that's a worst guess. Worst guess. Yeah. All right. So we finish our B.2 video here.